Section 4.6, Directional Derivatives, and the gradient. We've learned about partial derivatives, which basically measure the change in a function along either the x-axis or parallel to the y-axis. These are actually directional derivatives with a fixed direction. That's why we say the rate of change in the x direction or the rate of change in the y direction. Now in this section, we're going to learn about how to find the rate of change in a direction that's not parallel to the x-axis, not parallel to the y-axis, but instead a direction that we choose, given by a vector. So I have three different images here for you to look at. The one on the left is a partial derivative in the x direction, and we can see that the intersection of the surface and the plane y equals some constant, it generates this green curve, and that curve is basically a Calc 1 problem where we are looking at the rate of change along the intersection of the surface and the plane. And we can see that we're measuring change only in the x direction. In the middle image, we have the exact same surface, but I've changed the plane that we're using. So now I'm looking at a plane that's x equals some constant. The intersection is that green curve. We can see that as we measure the change along that green curve, we're only talking about change in the y direction, so parallel to the y-axis. Now in this section, we're going to talk about the image on the right, all the way to the right. And this is the same surface intersected with a plane that's parallel to the unit vector, sorry, not the unit vector, but the vector u that's given, the vector 1, 1. So this plane, this red plane, is intersecting the surface just like it did for the other two images. But notice that this red plane is not parallel to the x-axis. It's not parallel to the y-axis. Instead, it's parallel to a direction vector. So we can measure the change along the green curve, and this would tell us what the change is in the direction of the vector u. To start developing the definition of the directional derivatives, we're going to basically use the same thing that we did in Calc 1. So if you can think back that far. If you want to rebuild the image that I'm making on the right-hand side of the screen, you can follow the link at the top of the page to my GeoGebra project that will basically rebuild this whole thing for you piece by piece if you'd like. But I'm going to walk you through some screenshots. So the first thing that we'll do is start with a point on our surface. So you see I've added a green point onto our surface. And then we're going to choose a direction for us to travel in. And this direction vector is going to be given in the domain. So this vector is a 2D vector because our function f has two inputs, x and y. The function creates the output z. So the direction that we're going to travel in for this directional derivative is the vector u, and I've added that to the screen. It's a tiny little unit vector. We're going to travel in the direction of u for a distance of h units so that we can find another point on the surface. So I've created this dotted line on our surface, magenta color. We're going to travel along that line because that line is parallel to the vector u, and that line is on the surface. And we're going to find another point, the blue point, which is on that path. Then we'll create a secant line between these 2 points, just like you did in Calc 1 when you first learned about a derivative. You generated a secant line, and then you allowed the limit of the slope of the secant line for the distance between the points to go to 0. And that's exactly what we'll do. We'll let the points become closer and closer until they're right on top of each other. In other words, h is going to 0. And that will give us the formal definition of a directional derivative, which is what you see down at the bottom of our screen here. The notation is DUF. So you have a capital D that tells you it's a directional derivative. You have the vector u. This vector u is the vector that you're taking the derivative in the direction of. And then f is the name of the function. If you were working with a function that's not called f, maybe it's called g or h, then this notation would change. So the f just represents the name of the function there. Calculating this directional derivative essentially is just like we did in Calc 1, where you're finding the limit as h goes to 0 of the slope of our secant line. So take a shot at the GeoGebra link, play with it, and make sure that you fully understand how we're coming up with this limit definition. So just like we said on the slide with the 3 images, that a directional derivative is very similar to what we did when we learned partial derivatives. In fact, the directional derivative is a generalized partial derivative, meaning it's a partial derivative, but for any direction you choose, whereas the other partial derivatives we talked about were specifically in the x direction or in the y direction. Let's take a shot at calculating a directional derivative using this definition. Now, just like in Calc 1, you learn the formal definition and then you start to learn shortcuts. So of course, we're going to have to do the painful, long limit derivative definition at first, and then I'll have a shortcut for you in just a few moments. So for this problem, we're asked to find the directional derivative, DUF, of the function f in the direction of u. And then we're asked to calculate the value of it. So not only are we finding the derivative function, where we still have x's and y's, but then at the end we're going to evaluate that function at x equals -1, y equals 2. So let's start off with the pieces that we need. To calculate the directional derivative, we're going to use that limit definition. So we'll start with, get my marker ready. We will start with the limit as h goes to 0. Numerator has f of x plus h cosine theta, y plus h sine theta, minus f of xy, all divided by h. Now, there's going to be some extensive scratch work, and for the sake of keeping this video short and sweet, I'm going to refer you to the book to do the algebra portion of this. So you can refer to the book on page 424, and you can see how to get f at x plus h cosine theta, y plus h cosine theta, how to find out that that is in fact equal to x squared minus xy plus 3y squared plus 2xh over 5 plus 9h squared over 5 plus 21yh over 5. So the steps are shown on page 424 of how to simplify down to this value. One thing that might be easy to overlook or to forget is that we are given theta equal to arc cosine, or cosine inverse of 3/5. So we'll do that part of the scratch work. If we are told theta is arc cosine, or cosine inverse of 3/5, then we can take cosine of both sides to find that cosine theta is equal to 3/5. So anywhere we have cosine theta in our expression, we can replace that with the value 3/5. And then similarly, we can find sine theta using the relationship from the Pythagorean theorem. Simplify that down to look like this. So I would just replace cosine theta with 3/5 and find out that if cosine theta is 3/5, then sine theta would have to be 4/5. So anywhere you have sine theta in your expression, you'd replace that with 4/5. And then you would find this result. So work the algebra out, double check it with page 424, make sure that your work agrees with what the book is telling us. But in order to continue what we want to do, which is to calculate the directional derivative, I need to replace what I have in yellow brackets with what I have below in yellow brackets. But before I do that replacement, notice that we're going to do the yellow brackets minus f of xy. Maybe we ought to do that before we plug it into our numerator. So let's do that scratch work down here. We are doing everything in the yellow brackets, and then we're subtracting f of xy. Remember that f of xy has the terms x squared minus xy plus 3y squared. So whatever's in these yellow brackets, we'd like to remove x squared from that. We'd also like to remove negative xy from that, and we'd also like to remove a positive 3y squared, which all of those terms happen to show up right here. So when we subtract that off, we are left with the remaining terms, which is the 2xh over 5 plus 9h squared over 5 plus 21yh over 5. So our numerator, after all of our scratch work, simplifies down to these three terms. So let's go ahead and rewrite our limit, where we have 2xh over 5 plus 9h squared over 5 plus 21y squared over 5. Oh, I have yh, and somehow my brain decided to turn that into y squared. It's 21yh over 5. That's the numerator. The denominator was over h. If we try to plug in h goes to 0 right now, we would end up with an indeterminate form. So we're going to try and reduce. If we can simplify out a factor of h, we can divide it off and eliminate the problem of the indeterminate form. We have one h in the denominator. Every term in the numerator has an h, so we'll take off one factor of h from each term. That simplifies down so that our limit, as h goes to 0, looks like 2x over 5 plus 9h over 5 plus 21y over 5. If we let h go to 0, this middle term goes to 0 since it has an h left. And then we have 2x over 5 plus 21y over 5, or rather 2x plus 21y all over 5. This is our directional derivative. So the derivative in the direction of u of the function f, that derivative function looks like 2x plus 21y all over 5. But remember that there's two parts to this problem. Not only did we want to find that derivative function, we also want to evaluate it at x equals -1 and y equals 2. So we go ahead and plug those in. Replace the x with -1, the y with +2. We get -2 plus 42 over 5, or 40 over 5, which simplifies to 8. So this was an example of using the definition, the limit definition, to calculate a directional derivative. And remember that I said this is the tedious way of doing it. It is the rigorous and formal definition for the directional derivative, so we need to know how to do it. But of course, when it comes down to actually calculating these, there's going to be a shortcut for us. Stay tuned and get ready for the next video.